testing. I first want to introduce the idea. This is the deepest situation where you're thinking about evidence and what level of evidence should convince you. Saying it that way suggests the first of three analogies I'd like you to keep in mind, which is a court case. Of course, in a court case, you look at the evidence and you convict the person only if there's enough evidence that they're guilty. If there's insufficient evidence either way, or if there's sufficient evidence to convince you that they're innocent, then you do not convict. Your spam filter looks at each email that you get with kind of a similar point of view. It looks for evidence that it is spam, and it throws away or sticks into the junk folder any email that it finds sufficient evidence that it's junk mail. If there isn't sufficient evidence, whether because it's obviously not junk or because it just can't tell, it lets it pass through. A little bit different is what happens when you donate blood. They test your blood for HIV, and they will throw out the blood if there's evidence that it's infected. But if they're not sure, they will still throw out the blood. They would only keep it if there's a compelling case that it is not infected. In each of these cases, there's a hypothesis that you're gathering evidence for, that the person is guilty, that the email is junk, that the blood is infected. And if the evidence is strong enough, you take some kind of action. The hypothesis you are gathering evidence for and will take action if you're convinced of is called the alternate hypothesis, or HA. The opposite of the alternate hypothesis, that is, that you're innocent or that it's not spam or that the blood is uninfected, is called the null hypothesis, and that's written H sub 0. In general, in the absence of evidence, you'll carry on as if the null hypothesis were true, unless you're convinced otherwise. So the last case is a little more complicated. In each of these situations, though, here's what is unifying about them. There are two types of mistakes you can make. So in the court case, you can either falsely convict an innocent person, or you can falsely convict a guilty person. And they have very different consequences. There's nothing comparable about those two mistakes. You have to treat them separately. In this situation, you have a hypothesis you're gathering evidence for. You have a default hypothesis if you are unconvinced of that alternate hypothesis. And the consequences of the two different kinds of mistakes are not necessarily similar. There's a universal measure for how strong a given set of evidence is. You can see where that's an extremely general thing. How strong is the evidence for a proposition? This process of measuring the strength of evidence is called hypothesis testing. Anytime you measure the strength of the evidence, it's hypothesis testing. We will usually do something a little more precise. We will usually start ahead of time with a cutoff. How strong does it need to be before we are convinced? That cutoff, for reasons we will discuss later on, which are rather subtle, has to be set before you look at the evidence. When you pick that cutoff and use it to decide whether the evidence is convincing, this is called formal hypothesis testing, or more often significance testing. So we will usually do significance testing, but in general, the most general thing is hypothesis testing. And here is the basic principle. It's a little bit complicated, and we've seen echoes of it in the past. A piece of evidence is strong evidence for the alternate hypothesis if that evidence would be unlikely to happen if the alternate hypothesis weren't true. When you show the bloody shirt to the jury, you're implicitly telling them It is implausible that this person would have this bloody shirt were they not the murderer. If the alternate hypothesis weren't true, the thing we're seeing in front of us, a bloody shirt, would be unlikely. And the defense is going to try and argue there's some reason why that's a perfectly plausible, consistent thing with the defendant being innocent. When you think carefully about any evidence, this is what measures the strength of it. How implausible is the thing you're seeing given the alternate hypothesis isn't true? I have to apologize throughout this subject. The language, the ideas are rather complex, and the language is deeply contorted. Alternate hypotheses are the thing you're generally thinking about. We spend a lot of time thinking about the alternate hypothesis not being true, and it's quite contorted. So the p-value is the basic quantity we'll use to measure the strength of evidence. The p-value is the probability of getting data like you got in your sample, assuming the null hypothesis. Like you got is a phrase we'll have to unpack, but that's the basic idea. You assume the null hypothesis, you ask how likely is it to get something like what we've seen, and if it's very unlikely, if the p-value is small, then that's strong evidence that the alternate hypothesis is true and the null hypothesis is false. So the smaller the p-value, the stronger the evidence for your alternate hypothesis. What data like you got means depends on the alternate hypothesis, and it means you include any data that would be at least as good evidence for the alternate hypothesis as what you've seen. This is a difficult thing to process until we get to examples. Okay, we're going to learn a number of hypothesis testing procedures. They all have the same 5 steps. We're going to talk in general about hypothesis testing, which will have a fuzzy feeling, and I'll do an example which will give you a feel for what a calculation looks like. Next time we will turn that example into our first procedure, working with the categorical variable, when it will all become more concrete. And then we'll get to practice these ideas over and over again as we learn more hypothesis testing procedures. So the 5 steps in hypothesis testing. The first step are decide on your null and alternate hypothesis. These come from the question, and they are always statements about a parameter in the population. There are always some statement about mu or p or something like that. They will generally be of the form p or mu is equal to some quantity, or p or mu is greater than or less than or different from some quantity. For technical reasons, the null hypothesis always gets the equal sign. The alternate hypothesis always has a less than or greater than or different from, sometimes implicitly. Later tests will see statements about independence, which are only contain an equal sign in a subtle way. But conceptually, the null hypothesis is the default assumption, the thing you're going to assume in the absence of evidence, and the alternate hypothesis is the statement you are gathering evidence in support of. You're asking if your evidence supports. The second step, once you've decided on the null and alternate hypotheses, and I should say those are generally expressed symbolically when you do the calculation. You'll see what I mean in examples. Then you assume the null hypothesis. You assume what you would assume anyway in the absence of evidence. That's kind of natural. And you compute the sampling distribution of the test statistic. Each procedure will have some statistic that it uses to do the test. And we compute the sampling distribution. We've already done this, right? We've seen how to compute the sampling distribution of p hat and x bar. Those will cover our first 2 procedures. So that tells you what would happen if the null hypothesis were true, and now you relate it to what did happen. You compute a p-value, which is the probability of getting a test statistic like you got in your data, assuming the null hypothesis. I say again, like here, depends on what the alternate hypothesis is. It's the place where the alternate hypothesis enters into the procedure. So, step 3, we have computed a p-value. Step 4 is to draw conclusions. Remember, smaller p-value is strong evidence. So if the p-value is very small, then you view that as good evidence for the alternate hypothesis. In informal hypothesis testing, what very small is depends on what it seems like it should be to you. It's fuzzy, but in significance testing, it's completely precise. In significance testing, you are always given a cutoff, which is called the significance level, and is written alpha. The Greek letter alpha looks like a fish swimming to the left. It is usually a number like 1% or 5%, a small probability, 0.01 or 0.05 in decimals. And now here's the conclusion. If the p-value is less than the significance level, you conclude that data is significant evidence for the alternate hypothesis. If it's not, you conclude that data is not significant evidence for the alternate hypothesis. That's it. Okay? That's the basic, the final and most important step of formal hypothesis testing. And then step 5, the post-final step, is to check the assumptions. That will be familiar territory for you. I want to first run through an example where none of the calculations or math is involved. I just tell you what the p-value is to give you a feel about how these go. Then I'll do an example where we will compute the p-value. We'll kind of derive as we go from first principles. If that seems overwhelming, you will not be expected to do that. In the future, we will learn a procedure that covers that situation. So you start with an idea that you'd like to test. Your idea is that depressed people have lower body temperatures. If you take the temperature of a depressed person, it will be a little bit less than the standard healthy value, 98.6, which we all know in Fahrenheit. To turn that into a precise question, you have to make it a statement about a parameter. The obvious statement is about the average temperature of all adults with depression. Let's say with clinical depression, to make it a precise variable, or a precise population, I should say. So our population is all adults with clinical depression. Our variable is the temperature, and we are interested in the average, mu, of all adults with clinical depression of their body temperature. And now, our null hypothesis, the thing we would assume in the absence of evidence, is that what we've always been told to believe, the average body temperature is 98.6. Our alternate hypothesis is the thing we're gathering evidence for, that the average in this subpopulation, at least, is less than 98.6. How much less? We're not saying. Then notice the null hypothesis has an equal sign, the alternate hypothesis has a less than or greater than or not equal to it. All of that comes from your initial question. And we're going to do our test this time at the 1% significance level. Where does that come from? It will always be given to you in problems, and typically in real life where it comes from is the standards of the field. There's typically standard significance levels that people in a field or in a particular journal use and accept as the usual standard. How would you test this? Well, that's pretty obvious. You would go and find a sample of people with clinical depression, and you would take the temperature of everybody in your sample and find the average. So let's say we did that, and we found that X bar was 97.9. Now some calculation has to happen. We'll learn about that later. And let's say we end up with a p-value of 0.057. So what does that mean? That means that if mu were actually 98.6, if your initial guess was wrong and things are just the way everybody assumed, the chance that a sample would give an X bar of 97.9 or smaller is 5.7%. In other words, there's a 5 or 6% chance that you'd get that low of a sample average. So, sample average is a little bit lower than you'd expect, but not shocking. This isn't a really rare event, but it's not an incredibly usual event. So, to decide whether that's significant evidence, you compare it to your p-value. P-value is 0.01 in decimal. the p-value is 0.057 in decimals. The significance level is 0.01. Since the p-value is not less than the significance level, greater than or equal to, we conclude that this is not significant evidence. We have not found evidence for the initial position. This data should not convince us of it. We express that as follows. This is a formal statement. I'll describe the formal statement in more care when we get to individual procedures, but having gotten used to the formal statement of the confidence interval, this should not come as much of a surprise to you. The formal statement to conclude your significance test is this data is not significant evidence at the 1% significance level that average temperature of clinically depressed adults is less than 98.6. To atomize this, the sentence includes the conclusion that it's not significant evidence. If p-value had been less than the significance level, we would say it is significant evidence, otherwise no difference. It gives the significance level, which was 1%, given to us in the problem. And it gives the alternate hypothesis. I've put that in red everywhere it appears on here, because it appears in a couple of different places. The alternate hypothesis is that the average temperature of clinically depressed adults is less than 98.6. That's being said in words here, but it's being said up above when we described the process. HA mu is less than 98.6 is saying it symbolically. Mu is average temperature of clinically depressed adults, less than 98.6, and it's also being said less formally in the initial question. So the initial question becomes the formal alternate hypothesis. It gets written symbolically when you're doing the test, and it gets written in words when you draw the conclusion. And that alternate hypothesis has two pieces. One is the full parameter, the average temperature of clinically depressed adults. Still in that form, parameter, variable, population. And the other half is the comparison. That parameter is less than or greater than or different from some value. All right, so let's see where this comes from in a simple example. Our simple example is coin flipping. I've told you that most coins slightly favor heads. They come up heads a little bit more often than tails, so perhaps you want to test this hypothesis. So you take out a quarter, and you want to see if that coin favors heads. It's pretty clear how you gather evidence for that. You would flip it. Maybe you'd flip it 1,000 times, and let's say you did, and you got 550 heads. Again, that's more than half. So perhaps it suggests that the coin favors heads, but you certainly weren't expecting to get exactly 500. You were going to get a little bit more or a little bit less, no matter what. So is this enough more that it suggests that it favors heads, or is this just completely explainable by a fair coin and random chance? That's the question we're asking. This time we'll test at the 5% significance level. Don't get hung up on that. Those are just numbers. So we have to make this into a statement about a population and a parameter. And there's a little bit of a trick here. We're going to view our population as all possible flips of this coin. So when you flip a coin, you can think of that as randomly selecting one of the possible coin flips. If you think about it that way, then if the coin comes up heads 50% of the time, you're saying 50% of all those coin flips are heads. In other words, the parameter is the proportion of heads in all possible coin flips. We're looking for evidence that this proportion is more than 0.5, that it comes up heads more than half the time. So our alternate hypothesis is P, the population proportion, is greater than 0.5. So you see we've translated the initial notion of favors heads into a statement about a population proportion. And the null hypothesis is the default assumption that P is equal to 0.5, that it's a fair coin. This is the default assumption. It's what we'd assume in the absence of evidence. It also includes an equal sign. Okay? So we've sort of ignored the third possibility, that maybe it favors tails. We'll talk about that decision to ignore the third possibility later, as I keep saying. Okay, so we've done step one. We found the null and alternate hypothesis. Step two is we assume the null hypothesis. So we're going to assume that p is 0.5. So now we're in the situation of lecture 16. We have a categorical variable, we have a population, all coin flips, and we know p. We know the percentage of time. We're assuming that p is 0.5. So knowing p, we now know the distribution of the natural statistic p hat, which is the percentage of a sample of coin flips that come up heads. So assuming p equals 0.5, and let's presume for now that the assumptions are met, which they are, the sampling distribution of p hat is, what are the three facts? It's a normal distribution with a mean of p and a standard error of square root of p, 1 minus p over n. We know all those quantities. P is 0.5, because we're assuming the null hypothesis, n is 1,000. So we get that the average value for p hat is 0.5, and the standard deviation is 0.0158. And that tells us what would happen were we to do a sample of 1,000 coin flips, assuming the null hypothesis. Now we relate that subjunctive, what would happen if it were true, to what actually happened. What actually happened is we got a p hat of 0.55, because we got 550 heads out of 1,000 tries. So we're going to ask, assuming the null hypothesis, what's the probability of getting data like we got? Since our alternate hypothesis is p is greater than 0.5, if we had gotten more than 550 heads, if our p hat had been higher, that would be at least as strong evidence. So like we got here means at least 0.55. So our p-value is going to be the probability that p hat is greater than 0.55. If that sounded a little slippery, I can reassure you, first of all, this will be a procedure so you don't have to think it through each time. And second of all, when we go through it in detail, it will make more sense. But now, if you'll believe me that the right p-value to compute is p hat is greater than 0.5, now we're on completely safe and calm territory. This is lecture 16. It's a normal distribution, so we use 1 minus norm dist. 0.55 is the p hat we're comparing it to. 0.5 is the mean. Square root of 0.5 times 0.5 over 1,000 is the standard error. We always throw in that 1 for ritualistic reasons, and we get 0.00783%. That's a really tiny number. That's telling you that if the coin were fair, we could expect to get 550 heads out of 1,000 or more, one time in every 10,000 times you flipped 1,000 coins. It'd be an incredibly rare event. Okay? This is a formal hypothesis test, so step 4 is to compare the p-value to the significance level. The p-value, you can either do that as decimals or as percentages, but you have to do the same in both. That can be tricky. The p-value, 0.000783 as a decimal, is less than the significance level, 0.05. So, this data is significant, and we report. This data is significant evidence at the 5% level that the percentage of times this quarter comes up heads, that's the parameter, is more than 50%. In other words, this is significant evidence that the coin favors heads. That was our first hypothesis test. Next time, the process that we went through there, the reasoning, will be codified into a procedure for a hypothesis test about a proportion. After that, we'll codify the logic for a hypothesis test about a mean, where we could actually do the test about people's temperature that we talked about. And from there on, we'll learn more elaborate hypothesis tests and more elaborate confidence intervals to estimate and discuss various more interesting parameters, but the logic of hypothesis testing will never change. After we've done it a bit, because this is deep, I'll stop and talk more about this logic. But first, let me check the assumptions. Let me do step 5. the assumptions that we used, because we were doing lecture 16, the three assumptions are simple random sample, large population, and the rule of 15. Simple random sample, this was sort of subtle because we have this funny notion of the population is all possible coin flips. But if you think about the population is all possible coin flips and flipping a coin is just randomly selecting some one coin flip out of that population, then of course this is a simple random sample. That's how we'll view it. So we will treat flipping a coin as sampling from this abstract space, as a simple random sample from the abstract space. Large population, we would need there to be at least 20 times the sample size, so at least 20,000 possible coin flips in the coin, whatever that means, but there are infinitely many possible coin flips, so that's no problem. And finally, the rule of 15. Because it's a categorical variable, we do the rule of 15. Remember, here's a little bit of a subtlety. When we used lecture 16, we were assuming the null hypothesis. We were working with a p of, in this case, 0.5. So when you check the assumptions, you're assuming the null hypothesis. So when we ask, is np and n times 1 minus p greater than 15, you're looking at the p that the null hypothesis gives you, what we'll call the test proportion. So p is 0.5, n is 1,000, n times p and n times 1 minus p are both 500, and of course that's way more than 15, no problem. So all the assumptions are met here. Okay, so having watched lecture 21, you should be able to identify the 5 steps of hypothesis testing. That's just regurgitating. Should recognize and be able to distinguish, sorry about that typo, between the null and the alternate hypothesis in symbolic form, and go back and forth between symbolic form and verbal form. Null hypothesis can always be expressed as a parameter equals something, sometimes more involved where 2 different parameters are equal or something like that, but a null hypothesis will always have an equal sign. Alternate hypothesis will involve parameters and will always have less than, greater than, or different from, at least implicitly. The other thing to remember about the null and alternate hypothesis is the null hypothesis is the default assumption, what you'll continue to believe in the absence of evidence. The alternate hypothesis is the thing you're looking for evidence for, the potential new belief. And you should be able to go back and forth between the symbolic form, like mu is less than 98.6, and an English form, like the average temperature of all clinically depressed adults is less than 98.6. You should be able to interpret the p-value. P-value is the probability of seeing data like you're seeing, assuming the null hypothesis. Just for now, learn that phrase. We'll get more comfortable with it. And finally, given a p-value and a significance level, you should decide if the test is significant. P-value is less than the significance level, the test is significant. P-value is not less, the test is not significant. Those are the only 2 possible conclusions, and I'm going to be very pedantic about that wording, the use of the word significant and not significant in a significance test, and the non-use of that word when you're not doing a significance test. And you should be able to express the conclusion in a full English sentence, which, remember, identifies the conclusion, the significance level, and the alternate hypothesis, which is expressed to be about a full parameter and some comparison of that parameter.